Hey class, so we're gonna start off by just going over electrophilic aromatic substitutions. Um, so we've covered a bunch of different reactions, and I just want to point out the fact that like when the thing that makes we're kind of just gonna be moving forward in terms of the reactivity of alkenes, and so we've covered the reactivity of alkenes on their own and in conjugated systems, and this is the reaction that we would expect an alkene to have with something like X2. We would add across the double bond, and what we find is that when we have benzene, which is an aromatic system, that you don't get this type of addition across the double bond. And the question is why? Um, and one of the things that is even more peculiar is that if you add a catalyst to the reaction to kind of make the reaction a little easier, you don't actually get an addition reaction. Remember, you get a substitution reaction. So you're replacing a hydrogen on the aromatic ring with a bromine. So we call this reaction an electrophilic aromatic substitution reaction. And it turns out that you can do this, you can take an aromatic ring, a benzene ring, and you can do all kinds of different substitutions: bromine, chlorine, nitro, sulfonic acid, alkyl group, acyl group. Um, so just to kind of go over, remember, you have the double bond is a nucleophile. This is electrophilic. But unfortunately, in terms of the aromatic ring, the double bond of an aromatic ring is not electrophilic enough. So what we do is we take the bromine and react it with a Lewis acid to make something more reactive. And so when you take bromine and you react it with iron, you get iron tribromide, which is going to be the Lewis acid catalyst we're going to use in the halogenation reaction. So in the halogenation reaction, what happens is you have bromine that's going to attack the iron to make Lewis acid Lewis base complex. This bromine is a good leaving group at this point. This is the electrophilic bromine. And so essentially when you make this, what you're making is a very potent form of Br+. We call that the super electrophile. And then what happens is it's the same two steps in every electrophilic aromatic substitution reaction. You make the super electrophile, and then it's the same exact two steps. You do the nucleophilic attack to do the so the double bond attacks the electrophilic bromine, kicking out the leaving group. This is the rate determining step. This gives you something called we call the sigma complex. It gives you a resonance stabilized carbocation. And then you do an elimination reaction, so the Br minus, so this is essentially Br minus. The Br minus removes the proton, so you do a proton transfer and remake the double bond to give you back your aromatic ring as a substituted as a substituted product. So remember, it's the same two steps. It's the nucleophilic attack to do the addition step, right? So you're doing an addition step via nucleophilic attack, and then you're doing an elimination step via a proton transfer. It's the same two steps: addition, elimination, addition, elimination. Previous to those two steps is always the making of the super electrophile. And if you remember, we don't make the addition product here when you add Br2. And the reason is if you go back, technically this Br minus could attack that positively charged carbon, but the reason it doesn't is because the product from the addition reaction is less stable than the product from the substitution reaction. And so you can do this with other types of Lewis acids. You don't have to just use iron tribromide. The same thing happens with aluminum tribromide. So any kind of Lewis acid, and the reason why this is a Lewis acid is because the metal is electron deficient and is electrophilic and will accept electrons from nonmetals. You can do the same thing for chlorination. So if I just switch out the bromine for chlorine, and if I switch out the Lewis acid for some kind of Lewis acid with chlorines attached to it, you get the chlorination. This reaction doesn't work for fluorine or iodine. Fluorine's too reactive, iodine's too slow. And again, for the chlorination, it's the same two steps after you make the super electrophile. Nucleophilic, there's the addition step via nucleophilic attack. So attack here. And then you have the sigma complex. And notice that this sigma complex, this carbocation, is resonance stabilized. Right? So I move the double bond here, carbocation there, move the double bond here, carbocation there. And then I eliminate that proton to give me the double bond, to give me my aromatic system back. Make sure that you have practice drawing these resonance structures here, okay? So again, it's the same two steps. It's this two-step mechanism, nucleophilic attack followed by elimination. So we see the same thing in all the other electrophilic aromatic substitutions, and the only thing that's really changing is the identity of the superelectrophile. So for example, I can replace a hydrogen with a sulfonic acid group if I use fuming sulfuric acid. So fuming sulfuric acid contains sulfur trioxide. So in that sulfur trioxide, that actually has this kind of overlap here where there's this really big p orbital on the sulfur. And so they don't overlap all that well. So what that means is that sulfur actually ends up being somewhat, has a really big empty p orbital. So what happens here is that I have sulfur trioxide. That sulfur trioxide is the sulfur of the sulfur trioxide is electrophilic. So nucleophilic attack, that's the addition step to give me the sigma complex. And then I eliminate via water here, right, to give me my aromatic system back. And this anion is then protonated to give me the final product. So that's the sulfonation reaction. And the reason why the sulfonation reaction is interesting, and this will come up later, is that I can put the sulfonic acid, I can put this on via concentrated sulfuric acid, and then if I use dilute sulfuric acid, I can get rid of that sulfonic acid group and go back to the aromatic ring. And this is going to become useful later on in the chapter. We can put a nitro group on. In this case, I take a mixture of nitric acid and sulfuric acid. One of the things that students will do is they'll get this reaction mixed up with the sulfonation because they see the sulfuric acid. The difference between the sulfonation and the nitration is the presence of the nitric acid. So when I mix nitric acid and sulfuric acid together, what happens here is the sulfuric acid is more acidic than the nitric acid, so I actually protonate the nitric acid, so that's a proton transfer. This makes this a good leaving group. Remember, when I put a positive charge on the electronegative oxygen, that actually makes that oxygen more electronegative and wants it to leave. So this oxygen will kick down and kick out water to give the nitronium ion. That's the superelectrophile that we use in this case. Then it's the same two steps. The addition step via nucleophilic attack, and then the elimination step with water to give me back my aromatic ring. So that's the nitration. And then the reason the nitration reaction is interesting is because I can take the nitro group and I can reduce it. So remember, oxidation is when you're adding more oxygen to a molecule. Reduction is when you're adding more hydrogen to a molecule. So if I take a nitro group and I react it in the presence of iron or zinc, and then followed by base, I can take the nitro group and I can go to an amine, which is going to be very useful in terms of making a lot of interesting products. So in a three-step process, I can start with the aromatic ring, do the nitration, the nitric acid, sulfuric acid, that's the tip off that you're doing the nitration. Iron and zinc with an HCl, that's the reduction, and then the base is going to finish that reduction. The next reaction that we're going to cover is the Friedel-Crafts alkylation. So in the Friedel-Crafts alkylation, what happens is you take an aromatic ring with an alkyl halide, and I can substitute that hydrogen for an alkyl group. Similar to the halogenation, what happens here is that you need a Lewis acid catalyst. The halogen attacks the Lewis acid catalyst to give you this Lewis acid Lewis base complex. The positive charge on the electronegative atom makes it more electronegative and a really good leaving group. So this will then leave to give me the carbocation, which is now the superelectrophile. That carbocation will then be attacked by the aromatic ring to give you the sigma complex, which will you then eliminate a proton to give you the aromatic ring back and an alkyl group on there. You can do this with primary alkyl simple primary alkyl halides. And again, when you have the primary alkyl halides, what's thought to happen is you don't actually make the carbocation. This then just acts as a really good leaving group. One of the drawbacks of the Friedel-Crafts alkylation, though, is that because the reaction typically goes through what is thought to be a carbocation intermediate, if a rearrangement can occur to make a more stable carbocation, that will occur. So for example, in this case, if I take this alkyl halide, this primary alkyl halide, the chlorine attacks. Now this is a good leaving group. This can leave, and if this proton moves over as this leaves, I go from making a primary carbocation to a secondary carbocation, which is more stable. This then gets attacked by the aromatic ring to give you the major product. You would have thought that if I started with this, that I'm substituting, I'm attaching this carbon to this carbon. Notice that when you realize you're doing a Friedel-Crafts alkylation, what you want to be doing is attaching a carbon of the aromatic ring to the carbon that the halide is attached to. This only works, though, if you don't have the possibility of rearrangements. So a couple caveats in terms of the Friedel-Crafts alkylation. I have to have an sp3 hybridized carbon attached to the halogen. So vinyl halides won't work, aryl halides won't work. This carbon attached to the halogen has to be sp3 hybridized. Because this, and we'll go over this, because the first group actually makes the reactivity of the monosubstituted alkylated aromatic ring is actually much more reactive than benzene. So a lot of times you get polyalkylation. That means you add more than one alkyl group onto the aromatic ring. And also, some groups will shut down the Friedel-Crafts alkylation. So if I put something like a strong electron withdrawing group, I won't be able to do the reaction. Now, one of the things to think about, if we go back and we look, one of the things to kind of think about is how would we make a product if let's say I wanted to make this product, right? Now, we know that I can't, in the reverse, in the retrosynthesis, I can't go back starting from benzene plus my alkyl halide, like a primary alkyl halide. This won't work because this is going to rearrange to attach to this carbon. So I can't do this. So if I want to make this product, if this is the product I want to make, a question becomes, well, how do I actually make that product? And it turns out that in order to make this particular product, you have to go through a two-step sequence. You actually have to do what we call, like this product is going to come from the ketone. And then the ketone will come from what we call a Friedel-Crafts acylation. So if I take the aromatic ring and I react it with an acid chloride, I can connect these two things together via a Friedel-Crafts acylation. So this is what we call an alkyl group. An acyl group is where you have a carbonyl attached to an alkyl group. This is called an acylation. So if I replace a hydrogen on the aromatic ring with this group right here, if I replace the hydrogen on the aromatic ring with this group right here, that's what we call an acyl group. It's called an acylation, right? And so we can do that acylation in a very similar way as the alkylation. I can take the acid chloride with my aluminum trichloride. And what happens here is that just like in the alkylation, the chlorine attacks the aluminum, making this a good leaving group. This leaves, and I make what we call something that we call an acylium ion. And now this is my super electrophile. And so what happens here is that, and this is a resonance stabilized cation. So what happens here is that my aromatic ring does the addition step, attacks the carbon, kicks these electrons up. I make the sigma complex. That sigma complex then I eliminate a proton from that sigma complex to reestablish aromaticity, and I have my acyl product, my acylated product. The reason why the acylated product is interesting, more just beyond the fact that you're putting on a ketone, is the fact that I can take the acylated product and I can get rid of the carbonyl, right? So I can reduce the carbonyl. So remember, an oxidation is where I add more oxygen to a molecule. Reduction is where I'm basically replacing oxygens. A lot of times what you're doing is you're replacing oxygens or double bonds with hydrogens. So in this case, if I replace this oxygen with hydrogens, I do a reduction and I get the reduced products. These sets of reaction conditions are called the Clemmensen reduction. So if I want to make that molecule here, I can't do it via the straight alkylation reaction. I have to do a two-step process, right? I have to go through I have to do the acylation followed by the reduction. Because if I try to go from here, so if I try to just do this, if I try to react this with this, 1, 2, 3, 4, because remember, if I take that and I react it with this, I don't make this product. I'm not gonna make the bond here. This is gonna rearrange, and I'm gonna make the bond there. So the product that I actually make when I try to do the alkylation is I make this, right? And we don't want that. We want this. So if I want to make this, if I want to connect here, I have to go through an acylation followed by a reduction. And one of the nice things about the acylation is once you put this acyl group on, this kind of deactivates the ring and you don't get any more acylation. So you only get one type. The acylation only happens once. All right, so that's the end of just going over the different types of electrophilic aromatic substitutions. I hope that all made sense, and let me know if you have any questions. Thanks.